All right, today we're going to be talking about some more redox chemistry. Last week we learned how to assign oxidation states to carbon atoms in organic molecules, and we also had a little bit of a refresher on oxidation states for some of the other elements that we have in our compounds, as well as being able to recognize oxidation and reduction by both electron transfer and also looking at the structure. So one of the things we talked about was that if we're adding oxygen, that's going to be an increase in oxidation number. Conversely, if we're removing removing hydrogen, that's going to be an increase in oxidation number. If we're removing oxygen, that's going to be a decrease in oxidation number. And if we're adding hydrogen, it's going to be a decrease in oxidation number, okay? But I like to just remember adding oxygen increases the oxidation number, which I think is pretty easy to remember. And then all the other ones sort of flow from that. We briefly began talking about the alcohol oxidizing agents, but I just want to revisit that because that was at the very end of class. So I would like for you to have out your reaction list for the redox chemistry and organometallic reagents. This particular video is going to focus on reactions 1 through 5, which will be all of the alcohol oxidations. So we're going to first discuss reactions 1 and 2. I do realize there's a typo on the handout. At the very top where it's reaction 1 and 2, it says aqueous chromium oxidation, and then it says PCC, but this is actually not the PCC. Reaction 5 will be the PCC reaction. So I will go in and correct that error later, but I did just want to let you know about that. So briefly on Thursday, we talked about some of the alcohol oxidizing agents and specifically chromium-6. So if we're looking at reactions 1 and 2, this is going to be the aqueous chromium oxidizing agents. This will be chromium-6, which will have an orange color. And when it reacts with an alcohol, it will get reduced to chromium-3+, which is a green color, which is what we see in our chromic acid tests in the lab. And this will get oxidized to, depending upon the structure. So if it's a primary alcohol, it will go all the way to a carboxylic acid. And if it's a secondary alcohol, it will go to a ketone. So really this R is a little further out. So let's kind of correct that. So we've got our alpha carbon, and then we'll have our R group. And, you know, depending upon if it's primary or secondary, we might have 2 hydrogen atoms here or 1 hydrogen atom here. So this would be our R prime. If R prime equals H, that's going to be a primary alcohol. If R prime equals some sort of carbon group, that's going to be a secondary alcohol. And this will not work with tertiary. Okay, and hopefully that's obvious why, but one of the things we're doing here, this is an oxidation of this alpha carbon atom because we are removing hydrogen. So that's going to be an oxidation, and we have to have that hydrogen atom at the alpha carbon. If we have a tertiary carbon at the alpha carbon, then we don't have a hydrogen atom there. So does not work with tertiary alcohols because we need a hydrogen at the alpha carbon. So this would be R and R prime, and this would be from a secondary alcohol. Now, one of the issues here that I mentioned on Thursday is that the chromium 6 reagents have a lot of different ways that they're represented, unfortunately. And so we talked briefly about that on Friday. I'm going to revisit that today. So the way that some of the ways that the chromium 6 plus reagent can look, and this would be the aqueous versions. So on these, it might not tell you that there's water present, but there would be water present. So some possibilities, and I'm just going to list these as A, B, C, and D. But I believe there are probably more possibilities here. And that's going to be maybe combining sodium dichromate and sulfuric acid. Now, it doesn't say water here, but when making this, you would have diluted the sulfuric acid, so there would be water present. H2Cr2O7, which is technically what A is making. When we combine those, we're making this chromic acid. H2CrO4. So that's another chromium salt or chromium polyatomic ion source. And then another one you might see, and you might see it listed as just Jones. And what that is acetone, chromium 6 oxide, and sulfuric acid. And again, this doesn't say water, but that sulfuric acid would have been diluted with water. So all of these have water. Okay, so now let's look at how this would look, in a reaction if we had this listed out. So let's just do some examples here. All right, so if we have any sort of primary alcohol, we'll just take propanol as an example. And here we could list any of these reagents. We could list A, B, C, or D. So I'm just going to say that A, B, C, or D could be listed here. But let's just say it says Jones. All right. And so when we see Jones, what we should think to ourselves is, hey, that's a chromium 6 aqueous reagent. And when I have a primary alcohol, that's going to oxidize it all the way to a carboxylic acid. So again, if it helps, you can draw on the hydrogen atoms at the alpha position, and you know that we're removing one of the hydrogen atoms from the alpha position and the hydrogen atom from the alcohol. And so this is actually going to, again, get oxidized all the way to the chromium 6. Technically, what is first made is the aldehyde, but I'll show you in a minute what happens if there's any sort of water present. Then what's going to happen is the water is actually going to attack here, and then that oxygen gets protonated. I'm not going to show that step. And then, of course, the water here would get deprotonated. So this would be a nucleophilic addition plus 2 proton transfers. Now, you do not need to know this mechanism at all. In fact, for this entire chapter or this entire unit, you don't need to know any of the mechanisms except for the mechanism for that very last one, which is just a proton transfer. So this, you see here, you've got the hydroxyl groups present. What happens here is that this gets oxidized again. So you're going to remove the 2 hydrogen atoms, and that's how we end up with the carboxylic acid. Okay, so again, I'm not going to ask you to do this, draw this out or anything, but this is why the primary alcohol ends up going to the carboxylic acid when you have any of these aqueous oxidizing agents. It's because this reaction right here, this nucleophilic addition, is very favorable for aldehydes. Aldehydes are more reactive than ketones. And for those of you in the regular labs, you're going to see this play out, because if you have an aldehyde as your unknown, you might have a harder time getting a good boiling point or some other things like that, because it's so easy for it to oxidize to a carboxylic acid that some of your compound may have done that. And sometimes you even see it in the spectroscopy. So something to look out for if you have an aldehyde. Now, if we have a secondary alcohol, let's say we have something like this, and let's say this time instead we choose reagent C. Here, again, it doesn't really matter. All that matters is if we see any of these like this, basically anything but what we have for reaction 5, which is PCC, we're going to go ahead and do the oxidation, and if it's primary, we're going to end up with a carboxylic acid. Now here, with the secondary alcohol, we're going to get the ketone. And the reason for that is basically, shortly, we don't have another hydrogen atom at the alpha position that we could remove to further oxidize it to the carboxylic acid. So this is where we're going to stop. So this is technically reaction 1, and this is technically reaction 2 on your reaction list. However, really, they're the same reaction. Again, I'm not going to ask you to draw the mechanism for this. You can look in your textbook and see some of the, the mechanism is kind of shown there at least a little bit. Part of it is because it doesn't really affect the regiochemistry or the stereochemistry. The mechanism doesn't, but part of it is it's a little bit not well understood. So, yeah, we're just not gonna, this is gonna be kind of a strictly memorization reaction. So the main thing you need to know is that if you have a primary alcohol, that's gonna go to the carboxylic acid. If you have a secondary alcohol, and I'm going to remove my R group here just to remove any confusion, because, the alpha carbon here becomes the carbonyl carbon. And so then once we have the carbonyl, this becomes the alpha group. So the alpha group kind of shifts in this process because of the functional group change. And this will become a ketone. And as you're going to see in lab in the coming week, because this happens right here, if we have an aldehyde, that's also going to oxidize to a carboxylic acid. Now, chromium 6 is pretty selective. Now, it is toxic, which is definitely a big downside, but it is selective, so that means it's really typically just going to oxidize alcohols and aldehydes. And I mentioned that because in here in a minute, I'm going to do the next video, which will be on the potassium permanganate reagent. And for that one, you're going to see that it's going to oxidize additional functional groups as well as the aldehyde, the alcohols and the aldehydes. So that one is not going to be as selective. So there might be some situations where you would not want to choose it.